Hello everyone, welcome to my channel. You are learning with Dr. Shobha Nikam. In this video, I'll talk about design of MOD-5 Synchronous Up Counter. But before that, I request you all to subscribe to my channel. So here, counter is a circuit which counts number of clock pulses. So basic use of counter is to count number of clock pulses. This is up counter. It means it counts in upward direction 0 to n. It starts counting from 0 to n. So 0, 1, 2, 3, 4 in this way. This is synchronous counter. It means single external clock input is connected to all flip-flops. In case of asynchronous counters, external clock is given to one flip-flop and output of first flip-flop drives clock input of second. But here, single clock is connected to all flip-flops so that all flip-flops will generate output simultaneously. This is MOD-5 counter. It means it will count 5 clock pulses. So, number of states. How many states are there? 5. Number of states are 5. And range of this counter is from 0 to 4. You need to remember in digital systems we always start with 0. So 0 to 4 are 5. Then the number of flip-flops needed to design this circuitry. So one method is, this is my MOD-5 counter. So maximum count is 4. How to write 4 in binary? 1, 0, 0. How many bits are there? 3 bits. And to store 1 bit, we need 1 flip-flop. So here number of flip-flops needed are 3. Another method is n, number of states, must be less than and equals to 2 raised to n. 2 raised to n. Here small n indicates number of flip-flops. So if I'll put 4 here, 2. 2 raised to 2 is 4. But my number of states are 5. So 5 should be less than and equals to this value. So if I'll put 2, 2 raised to 2, 4. It does not satisfy the condition. So I need to put 3. 2 raised to 3 is 8. So number of flip-flops needed are 3. Now next we can design synchronous counters using any flip-flop, D flip-flop, T flip-flop, JK, any flip-flop. Whereas in asynchronous counters we generally use JK or T flip-flop. But in examination most of the times question is to design counter using JK flip-flop. So I will explain you how to design using JK flip-flop. And I will also tell you how to replace those JK flip-flops with T flip-flop. Design will remain same for JK and T. Okay, so first we'll draw the state diagram. State diagram for this counter. So state diagram tells us if this is my present output, what is my next state output is. Okay, so I'll start with 0, 0, 0. So if my present state is 0, 0, 0, that is 0. Then what is my next state? 1. After 0, 1 will come. After 1, 0, 1, 0, 2 will come. After that, 0, 1, 1, that is 3 will come. After 3, 1, 0, 0, 4 will come. So count is from 0 to 4 only. And after 4, again it will go back to 0, 0, 0. 5 will never come. So this is my state diagram. It means my circuit will rotate through these states only. Now let's start design. So we need 3 flip-flops. So I will have output Q0, Q1 and Q2. This is my present state. So let's understand, if my present state is 0, 0, 0. What is my next state? 0, 0, 1. So I will consider my next state also. In next state also I'll have 3 outputs, Q2, Q1, Q0 everywhere plus present state and next state. So I have 3 flip-flops. I need to identify inputs for all of them. So inputs for J2, K2, J1, K1, J0 and K0. For writing present states, I'll write simple truth table for 3 variables. 4 times zeros, 4 times 1, 0 0 1 1 0 0 1 1 0 1 0 1 0 1 0 1. Now, based on our state diagram, we'll complete this table. If present state is 0 0 0, my next state is 0 0 1. So I'll write 0 0 1 here. If present state is 0 0 1, next state is 0 1 0, that is 2. If present state is 2, next state is 3, 0 1 1. If present state is 3, next state is 4. What about 4? After 4, 5 will not come. What will come? 0 0 0. So here 0 0 0. 5, 6 and 7. For these 3 states, next state will never come because these states itself they will not come. So it is don't care, don't care, don't care. Now we know present inputs, we know present outputs, next state outputs. We need to identify which inputs I should apply so that I'll get these outputs. So do you remember excitation table? In excitation table, we have present state output, next state output, and from that we try to identify which inputs I should apply so that I'll get this result after this result. See, it is very, very simple and it is very important to remember excitation table. Excitation table tells us if I know my present output, if I know what I want after this output, which inputs I should apply. So excitation table for JK flip-flop is so here this is when present state is 0, next state is 0, J is 0, K is don't care. For 0 1, 1 don't care. For 1 0 it is don't care 1, and for 1 1 don't care 0. The link for a video for JK flip-flop is given in the description box. In that I have explained why if these are the present states and next states, why these inputs will come. So here, to understand or to find out values of J2 and K2, what we will do, we will compare Q2 with Q2 plus. It means we'll compare present state of Q2 with next state of Q2, and from that we will get values for J2 and K2. So here Q2 is 0, Q2 plus is also 0. So for 0 0, J is 0, K is don't care. Again 0 0, you need to compare Q2 0 0. So again 0 don't care. Again 0 0 0 don't care. Again 0 1 is 1 don't care. 1 0 is don't care 1. And then these three are don't cares. So here will come don't care, don't care, don't care, don't care and don't care. For J1 and K1, what we need to compare? We need to compare our Q1 with Q1 plus. So here 0 0. So for 0 0 it is 0 don't care. 0 1 1 don't care. 1 1 don't care 0. 1 0 don't care 1. 0 0 0 don't care. 0 don't care. So there are no such conditions. So don't care, don't care, don't care, don't care, don't care and then don't care. Similarly for J0 and K0, here Q0, Q0 plus 0 1 is 1 don't care. So in this way you need to complete this table. Now you have values for J2, K2, J1, K1, J0, K0. Next step is by putting these values into K-map, we will identify equations for these inputs. So we have 3 variables. So number of cells in K-map will be 2 raised to 3, that is 8. So let's identify for J2. So this is Q2, Q1, Q0. Number of cells are 8. 0, 1, we use gray code. So 0, 0, 0, 1, 1, 1, 1, 0. Here the values are like 0, 0, 0 is what? 0. 0, 0, 1 is 1. 0, 1, 1 is 3. 0, 1, 0 is 2. 1, 0, 0 is 4. Here it is 5. Here 6 and 7. So these are the values associated with these cells. So for J2, the values are 00001. That is for 000, it is 0. 001. So this is 0, 1, 2, 3, 4, 5, 6 and 7. So for 0, it is 0. For 1, 0. For 2, 0. For 3, 1. 0, 0, 0, 1 and then all remaining values are don't cares. So here the thing is you need to make groups of ones. So you can make groups of ones either with adjacent ones or overlapping ones. So there is only one and the beauty of don't care is you can consider them as 0 or 1 as per your requirement. So it is designer's choice to consider don't care as 0 or 1. So I have considered this don't care as 1 and remaining don't cares as 0. So equation for J2 is equals to here Q0 is 1, Q1 is also 1. So it is Q0 into Q1. So similarly, we'll make K-maps for other variables. So let's see for K2. So for K2 values are 4 times don't care, then 1 and then 3 don't cares. 4 times don't care and then 1 and again don't cares. And here we can consider all don't cares as 1 and we can make group of all of them. And when we can group all of them and when no cell is remaining, equation becomes 1. Equation is 1. Then next is for J1. For J1, 0, 1, don't care, 0, triple don't, 3 times don't care. So 0, 1, don't care, 0, don't care and then don't care. So here what we can do, we can make group of or chord, we call it as chord when we group 4 cells. So here equation becomes J1 is equals to, here what is common in these two, Q1 is 0, 1, so we'll not consider Q1. Q0 is 1 here and here also it is 1, so it becomes Q0. Here K2 is 1 and here J2 is Q0, Q1. Similarly, for K1, it is don't care, 0, 1 and then 4 times don't care. Don't care, 0, 1 and then 4 times don't care. Here also we can make a chord here. And same equation we'll get. K1 is equals for J0, it is 1, 1, don't care, 1, don't care, 0, don't care, don't care. So here we can group these two ones. So we can form a chord here and equation becomes J0 is equals to Q2 bar because value of Q2 is 0. Similarly for K0 values are don't care 1 and 4 don't cares. Don't care 1, don't care 1 and then 4 don't cares. So here also what we can do, we can group all of them together and equation becomes K0 is equals to 1. So now we have equations for each and every input. Then we can use these equations to draw the circuit diagram. These are the equations for 3 flip-flops. I will draw 3 JK flip-flops first. So let's assume this is my least significant bit and this is my most significant bit. It means this flip-flop generates LSB, this generates MSB. Then inputs will become J0, K0, Q0, Q0 bar, J1, K1, Q1 and Q1 bar, J2, K2, Q2 and Q2 bar. Here, this is my synchronous counter. It means single external clock is connected to all the flip-flops simultaneously. So, external clock is connected to all of them. So, clock is given. Next, we'll get outputs from here Q0, Q1 and Q2. Next is, see here, look at the equations. We'll start with J0 and K0. J0 is Q2 bar. So J0 is Q2 bar. I'll take Q2 bar from here and I'll connect it to J0. What about K0? K0 is 1. So I will connect this K0 to VCC or logic 1. Next, J1 and K1, both of them are connected to Q0. Q0. Okay, before that, see here also we want Q0 and Q1. So K2 is connected to VCC or logic 1 and J2 is connected to Q0 and Q1 multiplication of two of them. So I will use one AND gate. AND gate is used for multiplication. And output of that AND gate will go to J2. And inputs to that AND gate are Q0 and Q1. So one input is Q1 and other input is Q0. Then what is remaining? This J1 and K1 is remaining. So here I got Q0. So I will take Q0 from here and I will connect it to J1 and K1. So this is my circuit diagram. I will get outputs from Q0, Q1 and Q2. So these are my outputs Q0, Q1 and Q2. Now next step is let's draw the timing diagram. This is my clock input. Here I have shown negative age of the clock. Bubble indicates negative, arrow indicates age. You can use positive age also. You will get same output. So here negative age means falling age where transition is from 1 to 0. So I will get or my output will change at these instances. I have three outputs Q0, Q1 and Q2. Initially I'll assume all of them are 0. I will assume them 0. 0, 0, 0. So here Q2 is MSB. So value is 0, 0, 0. Next, we'll start with Q0. So Q0 depends on J0 and K0. K0 is connected to VCC. Then based on value of J0, our output will change. So J0 is Q2 bar. What is Q2? 0. Q2 bar is 1. So when J and K both are 1, in JK flip-flop both are 1, then next state is complement of present state. So here it will toggle. And similarly it will keep on toggling. I'll verify it again when we'll draw for K2. Then Q1 depends on values of J1 and K1. So J1 and K1 are Q0. What is Q0 here? 0. So in JK flip-flop, I'll write truth table again. 0, 0, 0, 1, 1, 0 and 1, 1. For 0, 0, next state is same as present state. For 1, 1, next state is complement of present state, and here it is 0, 1. So here Q1 depends on J1 and K1. J1 and K1 are same as Q0. So Q0 is 0. It means both inputs are 0. So next state will remain same as present state. So here it is 0. Then here you will say, see, Q0 is now 1. So J1 and K1 both are 1. So next state is complement of present output. So present output is 0. So next state will become 1. Here it is 0. So both inputs are 0. So next state will remain same as present. So present is 1. So next is also 1. Now Q0 is 1. So next state will toggle. Now for Q2, here what is J2? J2 is Q1 into Q0. Q1 into Q0. 0 into 0 is 0 and K is 0. So J0 and K1. K is 1. Then output is 0. Here also 1 into 0 is 0 and K is 1. So for 0, 1 it is again 0. Here also 0 into 1 is again 0. Condition is 0, 1, K1 and J 0. So next state output will remain same. 1 into 1 is 1. So now J is 1 and K is also 1. So next state is complement of present. Present is 0. So next will become 1. So here values are 0, 0, 0. Then this is 0, 0, 1, 0, 0, 1. 0, 1, 0, 0, 1, 0, 2. Then 0, 1, 1, that is 0, 1, 1 is 3. 1, 0, 0, that is 4. After 4, here see, Q0 depends on value of J0. J0 is Q2 bar. Q2 is 1. Bar of that is 0. So it is 0, 1. For 0, 1 output is 0. So here it will remain 0. Q1 depends on J1, K1. J1 and K1 are connected to Q0. What is Q0 now? Q0 is 0. So when both inputs are 0, next state will remain same as present. So present is 0. So next will also remain 0. This is 0. This is also 0. Then Q2. This is 1. But the J depends on multiplication of these two. So 0 into 0 is 0. For 0, 1, Qn plus 1 is 0. So here it will become 0. So see, after 4, next state is 0, 0, 0. And after 0, 0, 0, again these states will repeat based on the calculation just now shown. So here it will become 1. This will remain 0. This will remain 0. So it is 0, 0, 1. So in this way, MOD-5 synchronous up counter will work. See, this diagram is very easy. By putting values in this circuit, you will get this. Or otherwise, what you can do is draw the clock and draw this diagram from 0 to 4. After 4, you need to show that the next state is again 0. That's it. 0, 1, 2, 3, 4. Again 0, 1, 2, 3, 4. It will keep on repeating between these states. Thank you so much for watching. Press the like button, press the bell icon so that you'll get notification of my newly uploaded videos, and share this video with your friends. And don't forget to subscribe. Thank you so much for watching.